Okay, I'm Manhar, and I'm the structures group doing the wing design. So this is like a little overview. What I'm going to talk about briefly in this presentation, like about how I've come to design it, what kind of process I'm going through, the loading configuration, the internal structure. This is going to be the things which actually take the loads, and how I'm actually going to determine the loads which my calculations are based on. So this is the process I've taken. It's kind of like an out-in process. You first look at the whole wing, and then you say, let's size the main structural components. So these would be like the spars, the ribs, the stringers. And involved in this is the material selection. So for the moment, what I've done is I've taken everything to be made of aluminium, which sounds crazy, but the reason is it's a starting point, and then further on in that, I can then go and say, well, okay, let's look at the bottom of the wing. It's under tension mainly. This would be good for carbon fibre composites, and then kind of identify areas where I can whittle down the wing. So after I've got the main components, I go on to the individual components. This would be like, so for example, I have the stringer area. How exactly am I going to design the stringer? Like, what type of shape is it going to be? Is it going to be Z-shape, T-shape, so on? When you're looking at rib sizing, like, is it going to be are you going to have cutouts? Are you going to have trusses? Those types of things. Then going even further into the design, how am I going to join these things? So, you know, the spars will have spar webs and spar caps. How are they going to be joined? Are they going to be riveted? Are they going to be glued? How are they going to join up to each other? And then finally, it's the integration with the wing housing, which is with Carlos, and high lift devices. So how the flap mechanism and the slap mechanism will come into it. So if we look at the loading configuration, the main loading stuff all comes from a chord-wise pressure distribution, and this can be summarized as a lift and drag force and a moment at the aircraft's aerodynamic center. So this picture is looking along the chord. So if we then take a view at the front of the aircraft, it will give us a span-wise distribution of load. Now we've designed it to be, the aero guys have been designed it to be elliptical, and so what this will then give us a bending moment and a shear force distribution, which I can get from Tommy in the aero department. We also have a span-wise drag distribution, so this is looking top down onto the wing, and it just shows how at the moment I don't know what the drag distribution looks like, but it will be a variation along Y. We'll also get a moment distribution, as I showed from this bit over here, which will vary along the span of the wing, and this is just a torque, effectively, at each section. So those are the aero loads. Other loads which affect it will be the wing's weight itself and the fuel distribution. Now these two are actually kind of helpful when it comes to designing the structure because they counteract the lift that goes upwards, so it reduces the amount of load that your wing has to take. But for the worst case scenario, because it's very difficult to say what the wing's weight is going to be just straight from the off. So what I did was I just designed it purely due to the lift. So if it can take the lift, it will be able to take the lift minus the weight as well. Okay, so this is the internal structure of a basic wing, all the parts which you're going to take on it. We've got the cover skin, which is what the aerofoil shape comes from, spars, which are these things over here, stringers, and transverse ribs. They look puzzled together.
These are just saying which one's which. No.
Oh, okay. So yeah, so there's and I'll go on to spars and talk about them here. So these are span-wise components, and there are two kind of design philosophies. One of them is let the spar take all the bending, absolutely all of the bending, and the other side is let the spars take some of the bending and let some stringers take some of the bending. My approach would be saying let's have stringers as well. The reason for this is that the stringers, okay, you know, it's sufficient to have spars just carry the whole bending moment and the axial forces that come from it, but in terms of what it does to the skin when it comes to buckling, the stringers will help to reduce the effective panel size, so the stress required to buckle increases. So that's why I said let's take stringers as well. So spars. The spars are going to be made up of a spar web and a cap. So this would be the web over here, and these are the caps, top and bottom. My design at the moment has two spars, one at the front, one at the rear. These are about 20% of cord to about 70% of cord. They'll be based around what Rainus wants for integration with flaps and slats, as in they'll be how we attach them to those. That comes into effect exactly where they go. And the reason why I've gone for spar webs and spar caps as opposed to like a whole I-beam is that if you say that all the bending is going to be taken by the spar caps, then buckling will occur near to the ultimate stress. You can go to a higher ultimate stress because of the concentration of all the axial force of these areas. And then the web simply just takes a shear force. So this is what a cross-section of the wing will look like in between ribs. So this one we won't show a second spar, but this is the main spar, and this further beyond there will be the trailing edge. Like looking from books, structural books, it's given that the rear part of it takes no load, in terms of it takes no shear. So all of the shear is contained within this wing box section. And we can idealise it. So I've done a boom skin idealisation, and this is just based off coordinates that you can get. How long have I done it? 4 minutes. Yeah, boom skin idealisation. And I've assumed, booms take all the bending moments, skin takes all the shear stress. This is the equation for bending moments. So basically, the design is how do I size the boom areas, which is the issue. And these are tied up in the, these are tied up in the second moments of area. MX and MZ, Z and X. These coordinates and these values are all determined from loading and from the geometry of the airfoil at different sections. And so the way that you come about to do this in MATLAB is simply just by iterating over loads and loads of different. You start with a value and then you just iterate up until these are satisfied. And of course you can take the ultimate strength of aluminium to give you the final equation to solve this. And one of the things that I considered was at the top you're always going to be in a tensile compressive stress. So there's going to have to be more stringers in the top section, and the booms, which are idealised from the spar caps, will need to be slightly thicker. So that was greater area. The wing box skin thickness, so this is this part over here. How do we analyse that? This is just multi-cell tube theory that we learnt with Dr. Robinson. So given the shear force from the lift and the drag, which is applied in an airfoil section, we can calculate the open section shear flow. And of course, this is what we're looking for. We're looking for T, which is the skin thickness. Now knowing from just doing the course, the skin thickness in the spar webs is greater than the one of the actual skin going around it. So to accommodate for that, you just take that. I've said that the skin around this skin over here has a constant thickness, but this is 2 or 3, and it'll iterate 2 or 3 times this thickness over here to see whether it will satisfy well, I'll get to that. So now you have the closed section. Open section shear flow. You can calculate the open section shear flow by doing, this is the rate of twist. So if you find the rate of twist for the whole thing, you assume they're the same for every single cell. And of course this gives you one less equation that you need to solve. So the final one is just a moment's equilibrium with the shear force. And you have to assume for the moment, or I assumed, that the loads act at the shear centre. The aerodynamic centre is the shear centre. That's an assumption which is not very valid, but it's an assumption in the first stage. Tapering effects. The axial, of course, we've tapered the wing, so the axial forces in stringers and spars, they produce a vertical shear force. This is an extra bit in the analysis, which when we come to look at how to size the skin. And structurally, it's helpful for us because as we go down the width, this is showing bending moment against the span wide distance, it decreases, so effectively we can actually also taper our stringers as well. Do I have any more time? Okay. So stringers, as I said, these mentioned, these are span-wise components attached to the skin. They take some of the axial forces from bending, but their main job for me is to decrease the plate effective size to increase the critical buckling stress from plate theory. The ribs, these are chord-wise components. These things like maintain the airfoil structure. That's kind of one of their main jobs. This is one of their main jobs, to keep the airfoil structure. They transfer the aerodynamics loads, as I was talking about the pressure distribution, to the spar and the stringers. And again, this is another thing that they do. This also comes down to buckling, both of the stringers and of the plate. So the spars will divide up the spar beam into an acceptable amount of length to stop it buckling. And they also act as spars in a chord-wise system. So this distribution over here will also give you a lift distribution along the chord, and it's not great, it's not like a very big consideration, but it's a consideration I need to take into account. But the ribs will also act like a spar in a chord-wise sense. And how do we determine the loads? Well, initially I thought, let's try and look at the highest loading case, which would be takeoff or landing. Then I found that we use something called the load factor. This is given by N, which is L, which is just the lift over the weight. And when I mean the weight is fixed, it's the lift that changes. So during different maneuvers, lift will increase, and because of turning or inertial forces, and this is what N can take into account. It's governed by FAR 23 regulations, and we can develop like a flight envelope for what the load factor should be at different airspeeds. So the maximum for ours is 4.4, the load factor, and this is just applied onto the lift distribution. And these values are governed by FAR 23. That's where I got them from.